All right. Well, why don't we get started to give you the maximum time to be able to answer questions and go through this. Good morning and good evening for our Indian colleagues, and very early morning for folks from Hawaii. So we appreciate them being up here early to give us this webinar. The webinar is part of the Department of Energy UI Assist project. And today our talk is going to be an update on HNEI's research related to the renewable energy integration in Hawaii. And we have three speakers, Kevin Davies, Dax Matthews, and Chen. And so I'm going to turn it over to Dr. Davies to kind of get us started.
All right, thank you. Okay, so this presentation will be roughly divided up into thirds, right? Like I'll provide some overview of what we're going to, the context of renewable energy in Hawaii, and then some of our other efforts that are at least somewhat related to UI Assist, and then I'll turn it over to Dax Matthews for his work on the solar forecasting, and then Chen's work on the distribution system modeling. So the objectives today are just to summarize. I thought in the first third we'll summarize sort of the status of where renewable energy is in Hawaii and where it's headed. Maybe some unique pieces that people from outside maybe don't see right off, and then then we'll later dig into the more of the details of our research. So sorry, this is kind of wordy, but I thought some of these stats are kind of really speak to the situation in Hawaii. So we're right now at 35% renewable energy across the utility sector in Hawaii on an energy basis at the year level. So that is lowest on Oahu and highest on Kauai, but that shows some pretty significant progress. Like state mandate is to reach 100% by 2045. The peak renewable energy in some islands, particularly Kauai, has reached 100% for up to 5 hours per day. So they're doing that in combination of some hydro and then battery plus PV systems. And it's notable, the third bullet point here, it's pretty notable that the amount of distributed PV, particularly, that we have in Hawaii. So a fifth of residences have rooftop PV. That's over 3 times more than California on a penetration basis. So you have a lot of PV that is not directly controlled by a utility, and it's not even visible, as in the utility from an operations standpoint doesn't even know exactly how much PV is being generated at any point. And certain circuits are reaching their thresholds where they really can't accept any more PV without newer technology, non-wireless alternatives, and really trying to address the thermal and voltage limits that we're starting to hit. Meanwhile, I think we're starting to really see an uptick on energy storage and EVs. The latest tranche of power producer contracts out of Hawaii have been using PV plus energy storage across the board, and there is over 0.5 gigawatt of PV that's in the queue, like approved at the grid scale, along with 2.2 gigawatt hours of energy storage. And that may not seem like a lot for the mainland, when you think about the mainland, but just in context, Oahu is very much the largest load in Hawaii, but it peaks out, like our peak load, I think, is 1.2 gigawatts, right? So you see, and then the other islands are 100 or 200 megawatts at most. So that's a lot of PV, right? And the cost is significantly coming down to, these contracts some of them are even under 10 cents per kilowatt hour. So you're seeing it's just a combination of the technology getting cheaper along the learning curve to get this technology out there, and just the economics of energy being pretty expensive in Hawaii to start with. So I think we're really seeing the uptick of, there was a bit of a sort of a lull where initially we had a lot of we had net metering for PV on home use, and we couldn't continue that anymore because of just the economics of it aren't really feasible at much larger scale. So then they went to customer grid supply option, where you basically are kind of incentivized, or you look towards energy storage. And for a time, the PV uptake in Hawaii was kind of in a lull, but now I think the economics of the batteries are really getting to be where they need to be to take off again. We're seeing virtual power plant work take off, where certain entities are now contracting with customers to aggregate their services, especially the batteries, to do grid services. Okay. Some unique aspects here, like obviously Hawaii grids are islanded, and they're even islanded from each other. So just in the mainland, there's a lot of value to be had that each region is connected to another, and so somewhat they can buffer each other and provide resiliency against each other. And we don't have that here. There's quite a few other islands, island states and countries around the world that deal with these same things. Hawaii might be, I wonder, a bit more unique in that, first of all, distributed PV is rather high, but also I think we see really, I guess to summarize it, it's kind of the aloha spirit of just to focus on community and social equity and the environment. I think that's underpinning a lot of this. I think that's why we got the 2045 mandate, passed in the first place. And there's a lot of talk and discussion over, what's equitable as far as, the uptake of rooftop PV and who can afford it and who can't, and who benefits from it and who doesn't. So there's a lot of interesting discussion on the policy side that's coming out of that. Okay, so I wanted to now just cover a couple of projects that HNEI does at a very high level in Hawaii. These aren't within UI Assist, but some of it relates to that. We've had for quite a few years now a bunch of grid scale batteries that have been deployed across Hawaii. These have started on Hawaii Island, gone to Oahu, and now Molokai. And over the years, I think we've shifted different grid services that we're doing. First, frequency response for wind power smoothing, and then we got into voltage, real and reactive power control. And now on Molokai, some of the focus is on fast frequency response, because Molokai is a very small grid. It's about 5.9 megawatts peak, and it's traditionally been driven by diesel gensets. It also has around 2.5 megawatts of PV. And so just being that small of a grid and the really low inertia that it does have, fast frequency response is a big issue. And there's been work that HNEI has done along with the battery supplier to push the envelope as far as how fast that battery can respond. And it gets down into, how do you even detect frequency? Like, how do your phase lock loop, measure that frequency? Because if you can't measure the frequency well and stably and quickly, then you can't ever respond quickly to that. So there's more research to be done there. And then another unique aspect is this load bank that HNEI has installed and now turned over control to the utility. It basically is a resistive load bank that can be controlled fairly quickly to address the situations where you have too much PV and you're now pushing your diesel gensets below their minimal operating points. So that would be an unstable point. It also could violate EPA regulations because those diesel gensets might pollute more at those levels. So by putting this device in there, which really, it wastes energy, it burns off the energy as heat, it actually does allow more PV to be integrated on the grid, because the distributed PV that we have largely isn't controllable. So in those situations where it's producing too much PV, we have to get rid of the power somehow. Okay, and now another project I wanted to highlight. This project is ongoing. Like, our hardware is being developed. We're working on contracting to get things installed. It's a demonstration on University of Hawai campus with 2 electric vehicles charging stations. and these are bidirectional. So we can push and pull power and energy from the vehicles to support, optimization of grid services. And we have this layer where we are scheduling the vehicles, so that they're fleet vehicles, like they're used by the campus community. And people can go in and log in and say when they want the vehicle, how far they think they're going to drive, and we can calculate how much energy they think they need and what time. And that goes into the optimization algorithm for figuring out when is it best to charge or discharge the batteries, considering how much PV we predict that we're going to be producing and how much the other loads are going to be. Flipped. Okay, another project, third project I wanted to highlight before we get into the solar forecasting was a project around, it started out as power monitoring, right? Basically just, voltage and current monitoring at the RMS level for up to 3 phases, and trying to put forward a good piece of hardware that could do our instrumentation that we need in the field, particularly for distribution service transformers. We had projects going back to DOE, and Merrill Smith even knows about these, where we deployed quite a few commercial meters that we put inside other boxes and integrated with comms and power supplies and things like that to measure, power flow at a particular distribution grid in Hawaii. And that's data set that we now even are using with UI Assist collaboration. But that was pretty painful in terms of the cost that it took to keep the comms running, as well as even some of the equipment didn't measure reactive power in particular the way we would have liked for it to have. So we started realizing that we needed to take things a bit in our own hands and wanted to see whether we could build up a meter of our own that had that capability of keeping it low cost and also integrating communications kind of all one package with communication, power supply, measurement capabilities, and even some computing capabilities. So that's what we did starting in 2017, and we had a bunch of students involved. It was a pretty nice series of a couple project courses. And now we have a device that end to end we can measure voltage and current at fairly high resolution. Like we can get down to 8 kilohertz sampling, and then we have the full hardware and software up to the web interface to be able to see the final RMS data, and we can dive in at any level in that software and hardware stack to do whatever research we want. Like it has an FPGA, so we literally have control down to the gate level. We have a GPS that gives us very precise timing down to 10 nanoseconds, and so we're basically trying to use this platform more and more to do research. Currently, 2 things we're looking at is transformer health monitoring and PV hosting capacity. Trying to do PV hosting capacity on a more ongoing and granular level rather than like a batch, once a year kind of analysis that the utility might do. Can we do PV hosting capacity like an ongoing basis, like every day even, and give an estimate and of what the PV conditions are creating for the grid. Okay, so that's it for kind of the high level, highlighting some other projects, and now I'm going to turn it over to Dax for his section on forecasting.
Thanks, Kevin. So I'm going to give an update on the solar forecasting work we're doing at HNEI. I presented some of this in December of 2019, so this is going to be an update on some of the components, and I'll be discussing the operational forecasting system for the Hawaii domain, which has been operational now since October of last year. So it's been generating a forecast for Hawaii without any human intervention, and it's been running consistently pretty well. But just before that, just some background real quick. PV power is directly related to the irradiance striking the panel. It is the first order driver by far. Temperature and wind speed also have a secondary effect, but pretty much the irradiance drives the PV power production. Irradiance can be characterized by its path through the atmosphere. You have global horizontal irradiance, which is kind of the sum of all the irradiance striking the ground or a panel. that is made up of direct normal irradiance. That's irradiance that is directly traveling from the sun to the instrumentation or the panel. And then you have diffuse irradiance, which is the irradiance scattered by both the clear skies and by clouds. On the right here, these are observations from a test site that we have on Maui. Yep, there it goes, should be looping. This is at a 1 minute resolution. We have a pyranometer that measures global horizontal irradiance, a pyranometer measuring diffuse, and we have PV panels with monitoring instrumentation. So in that first top panel, sorry, I'm used to having a laser pointer or mouse control. In the top panel on the right, you see the GHI fluctuations. Directly underneath that, you have the power. And you can see those signals are almost identical. The yellow line in the background is output from a clear sky model. It's one of the models that we need for the forecasting. We have a solar geometry model that gives us the position of the sun, and then we have a model that describes the effects of the clear sky on the irradiance. And then observations provide the effects from clouds. So you see when it's clear sky, the observations follow the clear sky model pretty closely. The blue is what's been flagged as an observation, which we consider a clear sky, and then the red is a cloud-affected irradiance observation. The last two, or bottom two, is you can see the direct normal irradiance and diffuse below that. So direct normal irradiance is almost a binary. So when a cloud passes between the sun and the panel, direct normal drops significantly, and diffuse is kind of a constantly smooth signal, which when a cloud blocks the sun, you see a diffuse you'd expect. But there's also, when direct normal is clear and there is diffuse, you can have what's called cloud enhancement, and you can have irradiance well above the clear sky. You can see there's an example day in here where the irradiance and power output is so high that you can see like it reaches the inverter's threshold and it just flattens off. And it is, well, you can see the clear sky effects right there. And, well, oh, sorry, so next slide. Thanks, guys. So we've been building a system to predict irradiance and PV power on timescales from minutes to days ahead. To do this, we combine components. The first component is numerical weather prediction. It's WARF, for the Weather Research and Forecasting System, developed by NCAR. You need numerical weather prediction for forecasts longer than 6 hours ahead. There's too many processes that just need to be accounted for. Those forecasts are useful for planning and scheduling. On timescales, it's shorter than that. The satellite system kind of sits in the middle. It generates forecast from 10 minutes to 6 hours ahead. Both the numerical model and satellite forecast are a complete regional product. I'll show the spatial coverage in a second. The last very small scale local forecasting system is a sky imager system. So right now, the operational forecasting system for Hawaii is both the day ahead and hour ahead. The minute ahead system is still under development. On the right, you can see just a generalization of what the components cover in space and time. And the system is built so kind of numerical model passes information to the satellite system will pass information to the sky imager based system. Go to the next slide, please. So the next couple slides, I'll just talk about each component, and then the system that brings everything together. The final product is a probabilistic forecast which is a combination of all the information that we have. But as I said, the day-ahead forecasts are generated using WRF, which is developed by INCAR. We're actually using a flavor of WRF called WRF Solar, developed by Sue Hopp's group. WRF Solar is specifically designed for PV forecasting. It has more complex cloud physics parameterization. It generates all three components of irradiance, diffuse, direct, and GHI. It calculates irradiance at every single time step, whereas a normal model will kind of interpolate. Now we're running WRF. Operationally, we run WRF nightly. We generate a 4-day ahead forecast. And this is set up in a nested configuration. So here are the domains in the center there. You can see Hawaii, and the parent grid covers well past Hawaii. That is fed by information from GFS, or it's a global forecasting system. So we have a 25-kilometer global forecast, which drives that parent grid. The parent grid passes information to the child grid, which is the middle V02 grid, which is at a 1-kilometer resolution. The animations on the right are just showing the forecast from, I believe, 2 days ago. So today should be in there. The top figure is just surface winds in the meridian, or sorry, in the zonal direction. The middle panel is a vertical summation of the cloud fraction per level. Just the easiest way to see the clouds in the numerical model. And the bottom figure is the global horizontal irradiance forecast. Besides an irradiance forecast, the day-ahead system provides 40 temperature profiles, which are used to reference the satellite data, and also boundary conditions for the satellite forecast. And you can go to the next slide, please. So the hour-ahead system. So the hour-ahead uses both visible and infrared from geostationary satellites. We're using output from GOES West, which is one of 2 geostationary environmental satellites operated by NOAA. GOES East covers the continental US, and then GOES West covers the Pacific. GOES West is a brand new satellite. Well, it's a year and a half old now, but it's significantly improved capabilities from GOES 15. Well, sorry, it's now GOES 17. The previous satellite was GOES 15. But the new GOES West, GOES 17, provides significantly higher resolution space and time. Visible channel is at 500-meter resolution, and it provides a new set of images every 5 minutes. So it is a ton of data. The operational system generates a nowcast, or the state of the irradiance at the time of the image, as soon as it's available. So it's available about within 3 minutes of real time, and it generates a 6-hour ahead forecast from every new set of images. Let's see. And in the top panel, you can see an animation of the satellite output in the top and the left corner. Underneath that, you have the clearness index estimated from the satellite data, and the time series is irradiance observations versus the satellite information. At a site you can see in the lower right-hand corner, the little small circle is where we have instrumentation. So just showing you what the satellite is capturing versus observations.
Oops, sorry.
Both the satellites and sky imagers use a similar methodology for predictions. It uses a pattern tracking technique on coincident images to drive a vector field or a cloud motion field. And then from that applies an ejection fusion method to drive those clouds forward in time and generate an irradiance or power prediction. In the lower left, you can see a velocity field from 2 images. They've been overlaid, so the first image is in the blue, and then you can see the displacement of the cloud by the red, and the velocity field on top of that. Next slide. Perfect. So the minute-ahead forecast are from instrumentation that we've been developing in HNEI called ARIPS, the Affordable High Resolution Irradiance Prediction System. You can see that in the center panels. ARIPS is specifically designed for solar forecasting. It has a sky imager to find the cloud conditions. It also has a pyranometer to measure irradiance and other instrumentation to measure environmental conditions. It has a single board computer for doing some processing on board, microcontroller for monitoring or self-monitoring. The general idea of it was, it was supposed to be at a cost point where it can be deployed in clusters. So it's designed to be deployed in groups that work together. The main point of that is so it can apply stereo methods to find where the clouds are in a 3-dimension. So it can generate 3-dimensional cloud maps. In the center, you can see output from the sky imager, and then below that, you can see the derived cloud map. It applies methodology to find where the sun is, and then remove that from the image. So you can see the sun has been removed, and a lot of the effects of the sun have been removed from the image, and the clouds in gray have been identified very close to where the sun was in the image. The animation on the right is just showing you the procedure that attempts to find the sun. You can see the image is warped. It also applies methodology to figure out where the instrument is in space and correct for it. So the instrument was kind of tilted south, and it finds the sun and terrain around it to figure out exactly where it's pointed and then correct for it. Next slide. So recent work, and this is kind of the last big hurdle for ARIPS, is finishing the stereo cloud mapping. In previous versions, and we can still apply this now, we can use output from a oscillometer, which is an upward-looking LiDAR, and gives you cloud height directly above the instrument. So that's kind of a standard way. You take that point and you just kind of unwrap the image at that point and generate a 2D surface. What we're trying to do is develop full 3D cloud maps. So you can see in the top left, there's two images from 2 different ARIPS systems. Below that are the images projected to a normalized world coordinate system, and you can start to see how the system works. Those 2 clouds, you can see clouds in both images directly in front, and the system works like that. But finding those clouds in both images is again applying a pattern tracking technique, and then finding the vector where those points line up, and that gives you your reference point. On the right, you can see output from the algorithm. That small cloud directly in front is at about 2,000 meters. The rest of the clouds are much higher than that, and you can see that in the figure on the right. That small layer at 2,000 meters, and then big high-level clouds above that. All right, next slide. So all of this information is brought together using ensemble methods to generate a probabilistic forecast. So even without the satellite or sky imager products, let's say for today at any point in time and space, we already have 8 predictions from the previous days. So each night is generating the WRF is generating a 4-day ahead forecast. For Oahu, you have a parent and child grid. So we already have 8 guesses at what the irradiance is going to be at noon today for any point in the domain. As soon as the visible channel for goes west becomes available, as the sun is high enough in the sky, the system starts to generate a 6-hour ahead forecast from each new set of ghost images. So you can see kind of an animation of that in the lower left-hand corner. Each line represents a 6-hour ahead forecast from the satellite. You can see as time progresses and you have more and more forecast, it generates more and more predictions which make up your ensemble set. That combined with the numerical model, by 9 or 10 o'clock, at say an hour or 3 hours ahead, you now have 40 or 50 guesses. And then, so from that set, you can have a much more reliable estimate of the irradiance or the PV power, but you also can derive estimates of upcoming variability, and you can have a metric that defines the reliability of that forecast. On the right, you can see an animation of the PV forecast or the satellite forecast versus observations. The green line indicates now, so it's kind of skipping. Now it's stuck. Well, it's not really moving. Oh, sorry about this. But the black line, or let's see. The black line is the ensemble forecast. The small little gray lines is each individual 6-hour ahead forecast, and the red is the observations of irradiance through a single day. And so right now we're generating this operationally. Oh, you can go to the next slide. So this is just a similar output for instrumentation that we have on Oahu. But here we have observations of irradiance and PV power. And again, this is just showing the general behavior of the forecasting system. Okay, now the next slide. Okay, this is kind of an overview of the whole system. This has been running operationally since last October. So it starts with the WRF system, which pulls forecasts from the global forecasting system. It pulls sea surface temperature information and other climatological products. WRF then generates a 4-day ahead forecast that's each night. It provides 4D temperature fields and boundary conditions for the satellite system. It also provides forecast of surface conditions, of surface temperature and wind speed for the PV power model, and the day ahead readings. So as the sun comes up, the satellite system kicks off and begins generating 6-hour ahead forecast every 5 minutes at a 10-minute resolution. And that's driven from goes west. Let's see. The RIP system is in here, but it is not operational. It is still under development. Actually, and there's a missing arrow. Sorry, that 4D cloud and boundary conditions should be passed to RIPs. Let's see. But everything drives into the ensemble system, which collects the information and generates a probabilistic irradiance forecast. So the system is designed to be very quick past that. It is set up So once it's past the probabilistic irradiance forecast system, it's designed to take a list of distributed PV or pyranometers anywhere in Hawaii at any orientation, and then very quickly generate time series forecast of PV power. So right now it's generating operational products for the UH campus and for another test site that we have on the island of Hawaii where we have real-time observations. So it's constantly pulling real-time observations, then generating forecasts and comparing those forecasts against the observations. Again, this is all running without human intervention. And that's the state of the system right now. Oh, and that's all I have. Thanks.
All right, so we'll transition over to Yan now.
Okay, thank you, Kevin. So first, I would like to, the next slide, please. Yeah, so first I would like to briefly introduce our Advanced Power System Lab. So the goal is to test and validate power system operations and controls, especially to tackle renewable energy integration issues on the grids, and also to provide corresponding solutions. So the main equipments include the OPRT real-time simulator, Chroma 30 kVA AC/DC grid simulator, 2 transformers, a total of 35 kW rooftop PV system connected to 4 advanced PV inverters, AC/DC switchable test beds, and AC/DC programmable load banks. And for more details, please visit our website. So next slide, please. Yeah, so the next one, I will report some updates of our work under the same tool, the distribution system modeling and the benchmark system development. So the first test feeder is the Maui Meadows test feeder. This feeder is about 3 miles long and has very detailed secondary side information, include 104 single-phase service transformers. It altogether is 800 homes and around 300 PV systems, providing total 2 megawatts of distributed generation. So here we calculated the percentage penetration using the minimum daytime load. So the penetration level is around 205%. And for the data set, we have the scatter data with 4-second resolution, and the weather data includes the weather data is 1-second resolution, include the wind direction, the wind speed, temperature, humidity, and pressure, and so on. So next slide, please. So in the previous DOE project, we deployed about 60 high-resolution data collection devices to give us visibility at selected service transformers, PV inverters, and the customer meters. So from the inverter or transformer, it goes to a data accumulator, which is then sent to the server, which is located on our campus. So we collect voltage, current, real power, and rack power at so all this information at very high time resolution in order to capture the variability. So here is the example. The blue line, so on the left figure, the blue line is coming in as the 12 kV primary, and the triangle here is the service transformer. And the white lines are the secondary that goes to the customer homes. So in this example, we have the data monitoring points at 3 locations that are boxed in red, a transformer and 2 PV systems. So the figure on the right is a time synchronized plot at these 3 locations. So we have the PV system output in blue and orange, and the transformer load in blue. So here you can see that starting about 6 a.m., the transformer load becomes negative, which means that there is so much generation from the PV systems downstream that is backfeeding up to the transformers. So next slide, please. So before the UI Assist project, the Maui Meadows test feeder is modeled with the DW software. And for this project, we would like to run the model in OpenDSS, IFSysyn, and in Magazine. And considering the size of the test feeder, we need some automatic conversion tools to convert the model from one format to other formats. So we developed our own automatic method with the MATLAB script to translate the information from the DW to the OpenDSS. We validated the topology, the electrical parameters, and the power flow simulation. They produced basically equivalent results between the DW and the OpenDSS, these two software platforms. We also use the Ditto tool, which is developed by Unreal, and we made some modifications so it supports the newest version of the IFSysyn. And then we use the tool to convert the model from the OpenDSS to IFSysyn. And for the Magazine model, because it has the limits on the number of the simulated nodes. So we select a portion of the feeder and then develop the model manually. So the next slide, please. So here is a very simple example of the controller hardware in loop simulation to test some control algorithms. So our ARM device, which Kevin just introduced, can work as the power monitor and also as the controller. So the realistic model is loaded in OpenRT simulator. It sends the necessary measurements to the ARM device. And the ARM device can do some calculation to test the control algorithm and send back the control signal to the OpenRT as a closed loop. So next slide, please. The IFSysyn can accept different input files type, such as PSSE, SIME, Power Factory. In our case, we use the Excel file as the inputs. This model, it consists 104 single-phase transformers, 1,057 residential loads, multiple phase loads, and 295 small-scale rooftop PVs. So this model can be used in different scenarios. For example, it can be used to test the integration of the rooftop PVs into existing secondary, the low voltage distribution networks, and to test the different control and protection strategy with a few milliseconds time step in real time. So next slide, please. So depending on the specific applications, we can modify this model for different research purposes. So in this example, we just show the voltage magnitudes of two buses of the test feeder. So now back to Kevin. He will continue to introduce another test feeder located at the Molokai Island.
Mm-hmm. Yeah, so in the original UI Assist, we had said that we would develop more than one model, the first model being the Maui Meadows, but also we wanted to draw on Molokai. Molokai, again, like I said, is a small island with a peak power of around 6 megawatts. And we don't have the detailed models that we do on Maui Meadows, but we do have information on all the primary circuits down to the transformer, but not below the transformers, service transformers across the island. And that again is in DEW. We can go about the same process now that we've develop that for Maui Meadows, we can use that same process to convert the Molokai over to ePhaser sim, and that's our plan. There may be some more software issues to develop because it is a kind of a custom tool, but we don't expect any big issues there. But I wanted to bring up sort of another possibility and thing that we will be doing, at least outside UI Assist, or continuing to do outside, is rather than looking at power flow systems and RMS type models, we can look further into the frequency dynamics in particular on that island, because it's pretty interesting that it's a low inertia grid that is has a reasonable amount of PV and load changing, and the diesel gensets are trying to regulate frequency, but meanwhile the PV is taking a larger and larger role, and we have the battery that's trying to also regulate frequency, and so there's a lot of interplay there. We have models. We have a PSCAD model, detailed PSCAD model from the utility. Maybe some questions about how much of it can we use or hand over, but we do have that for reference at least, and we have developed on a separate project a simplified Simulink type model of the grid dynamics that is fairly accurate in capturing the what's happening when load changes, and so that is a possibility to use that type of model for UI Assist. I mean, honestly, we were kind of resource constrained on how much we can throw at UI Assist, but it could be possibly even a more interesting model rather than distribution power flow model, which is not that unique on Molokai. It's just it could be anywhere with a lot of PV. It doesn't really capture so much of the island nature. We could instead focus a bit more on modeling the grid dynamics, which are very unique for Molokai. So that might be some more discussion. I'm not saying change course, but I'm just saying if there's other partners in the team that might be interested in looking at that with us, then maybe we'd be inclined to involve more of that work. Okay, so I wanted to show at least two, or give the links to two web resources. I'm not going to go to these websites right now, but basically the first one is capturing Dax's forecasting system, and you can go to that link and see it. The second link, actually, you'll have to ask me for a password. I'm just not very sure if that website, if I release it to the world, then I don't know, we might take it down. So if you're interested in seeing this one, the second one is monitoring using that argument system, like in some cases modeling monitoring power flow for a load or device, and then in some cases we have it configured to actually query inverters or even grid batteries using standard protocols, and then report that data out. So, and there's a web interface there to visualize and shift through the data and download it. There's also, not shown here, a whole real-time system behind it, so that whenever data is logged or measured by that system, it propagates very quickly, low latency through the system. It uses a publish subscribe type communication system, so we literally can get latencies that are more or less just dictated by the internet itself. We tested it from demonstrated in Alaska, and we had 58 milliseconds back to Hawaii, literally from the time the data was measured to when it showed up on the server. So we can get into some pretty high resolution things, and with UI Assist, at least in the original proposal, we said that we would try to provide this PV data in a real-time streaming type environment, so that then we could hook that into a simulation environment. And we've done that on our own, so we're fully capable of making that linkage. We have Simulink Simulink block that will over TCP/IP or UDP, we can read that data and present it to the Simulink model, which can go into real-time simulation. I guess the real question is, what do we want to do with it? I think the original vision was that information, along with the forecasting of the same site, could be used with some algorithms and control, and that was with other partners we need to probably continue that discussion and hand it off to the right people so that we maybe integrate that capability. All right, and so just the final sort of conclusion slide. We've covered sort of the state of renewable energy in Hawaii. We talked about some of the things that HNEI is contributing to that, and then went into our major UI assist work. We wanted to deliver a couple of points of collaboration or needs that we have. Like, we're limited in our real-time simulation platform to 1,000 nodes or buses, and so we actually cannot simulate the full E-phasor sim model of Maui Meadows because it's 1,400 models or 1,400 nodes. So we want to find a partner. I think Burns and McDonnell I think earlier on had offered maybe to help validate models or to test models. We need to find a partner that might be willing to run that model and kind of check it out at the full sense, because otherwise we have to trim off a subset of it. And then beyond that, more at a research level, I think there's a lot of interesting things that we can build off of that. That the whole thing I just said of using real-time streaming PV data and forecast at the same time, like what optimization and control can we do off of that. And then I think Dax, probably an offline discussion, but he's been moving a bit into integrating some more machine learning into his process. So he has a lot of insight on where machine learning can be best used to improve that system. And then, with the real-time simulation platform, and there's a lot of questions to be answered as far as the impact of PV penetration, state estimation, model simplification. I think all these are, interesting areas that can be done off of the Maui Meadows model in particular. So that's it for the presentation. I'll just, show our contact information, and I think we do have a reasonable amount. Well, no, we don't have a lot of time left for questions, maybe at least 5 minutes, but let's use that time and open up any discussion we can. Brenna, do you have any questions that people have commented on that you want to bring up, or do we just have somebody speak up whenever they want to? I'll try to go through. I see written questions now that I can bring it up. I don't know how to decide which ones are best to address first.
I think there's 3 questions right now. So
okay.
So the first one is, can this forecasting model work in other places in the world, say India, or would we have to change certain parameters?
Okay, Dax, can you speak to that?
I can. We've developed system. We've applied the system to a few different domains outside of Hawaii. The first, just a couple sites on the mainland, but we have also applied it to Thailand and Korea, using Himawari 8, which is a Japanese satellite, and COMS 1, which is a Korean satellite. The WRF can be applied anywhere. You just have to build a grid and then figure out the best parameterization that describes that atmosphere. But the satellite system, all you really need is access to satellite data. There's geostationary satellites covering every portion of the world right now. It's only just if you can get to that data. I'm not sure exactly which satellites cover India. I know there's some Russian satellites in that area, but I'm not sure if there's any European satellites. From what little I've looked into it, the Russian satellites, that data is not available, but some of the European may be. And it's actually possible that Japan or the Japanese or Korean satellites might provide coverage, but that's probably on the edge of scan. But it's possible.
Great. Okay, the next question is, you said there's a Simulink model for charging 2 inverters regarding the transformer connections. Which ones are you utilizing for the 3 transformers, and at what power levels and voltage levels?
Okay, sounds like somebody I think level. I think it was it this slide? Somebody tell me. Was it this slide we're talking about? You said early in the presentation. Do you think this was slide 6? Simulate. The only thing that's throwing me off is it's for charge. It says for charging 2 inverters, but it's for charging 2 batteries, and it's really small. So I'm not sure whether they're interpreting all that from that small diagram or not. And the question is, I have a question regarding transformer connections. Which ones are they utilizing for the 3 transformers? Okay. I'm really struggling to make the connection that this is the diagram that they were bringing up. It is a Simulink diagram. Maybe we could have that user clarify like which slide, if it was this slide, or we can move on to the next question while we do that.
Okay, there are a couple more questions in here. Let's see. Social equity. There's a question about social equity. Has there been a push towards adopting residential battery storage to enhance resiliency for vulnerable households in the community?
I was just still thinking about that last question. If you don't mind, I think I can answer it real quick. Do you mind if I just do that real quick? I think I now understand the question, and that it isn't that slide. I'm pretty sure.
Okay, go ahead.
I think it's the lab diagram, because it's talking about 3 inverters and transformers. I think it's this one, right? What we have with the inverters is we have 3 single-phase inverters and 1 3-phase inverter hooked up to subarrays on a PV array that's on the roof, and we have 2 different grid transformers that we can connect to with a switch. So we can run our hardware in a loop system on really one of 3 things. One is the regenerative grid simulator that can produce AC or DC, grid situation up to 30 kVA. And then this option B is a 3-phase, 480-208Y type system, which has its own drive pack transformer hooked into our lab. The third option is a split-phase transformer. So we can choose between those, and the voltages there are shown. Those are standard US voltages, for split-phase and 3-phase. I think that was more of what the question was, but again, we can revisit it. Okay, so now with whatever time we left, let's go back to the next question there.
Yeah, I think the question's more about social equity. As we look at the new National Academies report, they talk about some of the renewable and green energy related to socioeconomics and not being just about people that can afford it, but helping the general population. So I think the question is about storage in communities for vulnerable households related to resiliency.
Yeah, and if I read a little bit behind it, it's maybe we're kind of saying, well, if a customer has enough money to buy a battery, they're probably one of the more fortunate ones. And can their resiliency that they have because of that battery support the larger community? Is that maybe what's behind the question?
Yeah, I think that the question is, how do we help vulnerable households that may not have the finances to have a backup generator or battery to still have resiliency?
Yeah,
but Thomas, I don't know if you want to add to that.
I think it's a totally. Oh, you said you want me to add to it, or I'm sorry.
Well, I didn't know if Thomas wants to add the person that asked the question.
Sure.
Okay, go ahead, Kevin.
Well, I mean, yeah, it's a totally open question. I mean, it on one level, it's a technical issue, right? Like, because the way it's worked out right now, at least in Hawaii, is when the grid goes down, and you have a battery. If it's a grid forming type battery, it'll power your house, but it by the technical configuration as well as what it's by contract it's not supposed to export grid power onto the grid, because you can end up with a safety issue towards utility line workers, that you're exporting power to the grid when the line workers think that the grid is down. So there's it's kind of a multi-pronged challenge. Like, in theory, yeah, you could have your contactors and your battery control set up so that it could form a grid in that manner and export onto the grid. You then would have an issue of all these batteries that are residential sized. They would have, and then they're in grid forming mode, but they have to be in grid forming mode together now, which is a whole nother issue. Like, you're creating a microgrid that is driven by these batteries, which are not right now meant to be cooperating really. And then you're exporting power onto the grid with possible safety issue. And then the third issue, which is more the economics maybe, is is that just a altruistic thing? Like, the people that have the battery, they're just required to do that to serve the rest of the community because that's the right thing to do? Or are they compensated for it? And if so, how? There's so many levels, and I think it's an excellent question. I think it's where we need to move with things like this, but it just is, it's really tough for all these reasons,
Yeah, good. Thanks for that. So a couple questions from Sanjeev. The voltage rise issues at the PCC as they are distributed, solar PV with different capacities, since load may not follow an output curve. I guess there's a question about the voltage rises. And then how do you perform load sinks since more residential load comes after sunset? Are there pricing mechanisms for that?
Okay, so the voltage rise issue, question number one, Yan maybe has the best situated to talk to that. I mean, she looked at it specifically. I mean, voltage does get affected, but do you have a few comments on that, Yan?
Yes, I mean, for sure, with different capacity of the solar PV, we see the voltage rise issues. So I think that's why we kind of some research focused on the smart PV inverter control, which can improve the voltage rise issues.
But yes, so in general, load, only a subset of the load is able to follow the curve, right? Because certain appliances now are maybe more controllable, water heaters and some other things, but for the large part, your PV is not, your load's not going to follow your PV. And in Hawaii, there are different interconnection rules. Like the earlier ones were net metering, so whatever excess you produced over top of what you needed, it would just be exported, and of course that would have impact on voltage directly. Then then there's evolution towards customer self-supply, which means that you're not allowed to export at all. So if you have the ability to produce too much more of the PV than you need to use, you need to have your PV inverter curtail that energy and not actually produce in the first place. And then the other one is customer grid supply, where you can put power out onto the grid, but you're not paid, as much for that power you put out as the power that you buy from the grid, right? So I think, it starts to be, with the customer grid supply especially, it starts to become an incentive for the customer to try to match their load with their PV production, right? So there's a little bit of incentive there to start moving that direction. And then I'm maybe more specifically into the voltage rise issue, at least in Hawaii and I'm assuming in other states. There's some settings in these smart inverters to do volt var compensation. So at least in Hawaii, there's a dead band around like the nominal voltage range, so that in normal operation you're not going to be injecting or sinking reactive power, but then when voltage starts to become out of bounds or high or low, then it injects or sinks reactive power to help with that voltage rise and sink issue. That is not coordinated, so that's like kind of just a local decision of the individual inverter. There's no coordination or optimal power flow among inverters really in the field. Second question, how do you perform load sync since more residential load comes after sunsets? Are there any pricing mechanisms for that? Well, I mean, I maybe barely touched on that with that customer grid supply thing, right? Like, you know, when you're getting paid less for the export versus the import, right? So during the day when you're exporting, you're getting paid less from the, you know, the PV power you're producing. So there's a mechanism that you would want to shift your power usage. In Hawaii, you know, we are moving towards the option. I think there is formally the option to enroll in a time of use pricing as a residential customer, and in that case, they'll swap out your meter for a smart meter, and they'll you know, figure out your time of use of power, not just your actual your total energy use, and they'll be priced according to a certain schedule, and you know, that would then provide an incentive for customers to, you know, use more power, shift more of their power usage during the day. You know, if there's activities they can shift to the day. You know, as it is right now, I don't think a lot of customers are going to be jumping on that. I mean, in my quick read through of it, it's not something that a typical customer may want to be doing, because unless you have some activity that you can easily shift to the day, you probably aren't it's probably not the best economic decision for you. But that time of use, you know, issue like that time of use thing opens up the possibility to even, you know, buy a battery and generate revenue. Like if you could somehow, if you're on a time of use system where you can, you know, do energy arbitrage essentially, then if you got a cheap enough battery, you could buy energy when it's cheap and sell it when it's expensive, and you could make money off of that, right? I don't think the battery technology is there to, you know, cheap enough yet for that. Anyway, that's it about that. I mean, I guess people are probably going to be dropping off here, which is fine, but maybe should we continue through the questions or not?
So I think why don't we do one more, and then we can. I think you put your contact information in on the slide, that if people have further questions, they can reach out to you.
Yeah. Okay. So the one where if we just go in order, I think it's Ahmed Saber had a question about 105% penetration. That 105% penetration was in terms of daytime minimal load. So your minimal load during the daytime when everybody maybe is at work and away from their home, the PV capacity to generate power is 205% of that minimal. So, you know, it kind of would follow, at least imply, that that's going to be exporting power, right? You know, exporting maybe up to 100% or half of the PV is going to be exported. And he's asking about voltage and harmonics. You know, I think voltage we already kind of talked about, that, you know, when you're exporting power, you definitely are reversing power flow and therefore reversing, you know, the effect of Ohm's law, that you're going to, you know, cause a voltage rise. The harmonics, I think, are a whole nother thing. We typically haven't been researching into harmonics as a group, but, you know, there's a lot to be done there. I think the inverters are pretty advanced now, that they're pretty low harmonic inverters, but you know, I think there's a lot of research elsewhere on what the inverters are doing for harmonics, and what inverter-based, you know, power grids are, the effect that inverter-based, you know, power sources are having on the grid. Well, I guess that's maybe all we can cover right now, right?
Oh, well, that was pretty awesome. So there's a lot of great information in there. Thanks for doing the Q&A.
Yeah.
As people have questions, please feel free to reach out to Kevin and his team. But Kevin, we appreciate particularly getting up early and presenting, and a lot of great information in the presentation. So thank you so much to Yen, Dax, and yourself for a great presentation.
Okay, thank you.
Thanks for the questions, and thanks for participating. And we will not have a workshop a seminar in May or June, as we will be moving to our theme lead meetings. And then